presenting.
Hello again, everyone. I'm Joe Pryweller, Senior Director of Conference Content for Plastics News. I want to welcome you to this webinar presented by Husky Technologies and organized by Plastics News. Liquid silicone rubber applications are gaining popularity among injection molders to meet the needs of customers as medical, technical, and automotive brands expand their product portfolio to take advantage of this material's unique properties. Due to rising material costs and the inability to use regrind, the benefits of direct gating with runnerless molding have become more compelling. This webinar will address the benefits of runnerless molding for LSR. Let me introduce today's presenter. Derek Hennebeek is the Hot Runner Product Manager for Husky Technologies and is currently responsible for new product launches, specialty applications, and product portfolio management. With over 20 years of experience in manufacturing and plastics applications, Derek specializes in hot runner technology and injection molding. During the course of the webinar, you can ask questions by opening the Q&A icon located at the bottom or the top of your computer screen and then typing in your question. Your question will be asked in the order that it is received after the presentation portion of the webinar is completed. Let me now turn the presentation over to Derek Hennebeek of Husky. Derek, the floor is yours.
Thank you for that introduction, Joe. It's great to have everybody here today, and I would like to thank everybody for attending. I really look forward to sharing what we do with so many people today. So over the past few years, Husky has received several questions and inquiries about materials like LSR and technologies like cold deck. And we've since developed a cold deck design with field testing and refinement through customer partnership and feedback. And everything we've learned along the way is what I'll talk about today. So over the next 20 to 25 minutes or so, we'll cover several topics. First, an introduction to Husky Technologies, as in who we are and what we do. Then we'll talk about LSR, or liquid silicone rubber, its place in the market, its growing use in today's world, and molding considerations. We'll go over the benefits of direct gating, and then the requirements of a good cold deck design, including the driving features behind Husky's cold deck technology. Husky is an industry-leading company who manufactures injection molding equipment and provides services around the world. We design and supply hot runners and temperature controllers for mold makers, converters, and brand owners. And we utilize standardized engineering and manufacturing to ensure consistent product and performance anywhere in the world. And all of this drives our goal to be the highest quality provider of the world's most reliable hot runners, cold decks, and controllers. We are a global company with headquarters just outside Toronto, Canada. We have manufacturing facilities in the United States, Luxembourg, Switzerland, India, and China. We have additional tech centers, spare part centers, and sales offices in several locations of the world, with Husky sales and service experts everywhere in between all of these pins and labels. This infrastructure allows us to understand and meet customer unique needs worldwide, and to do that at the local level. Now, when it comes to design and manufacturing, we serve a variety of market segments and configurations. Each has their own unique solution when it comes to thermal management and application needs. We'll start with single drops, which function as machine nozzle extensions for prototyping, low cavitation hot runners, which are typically used for parts with intricate mold actions like device housings, and high cavitation hot runners for molds built to support extremely high output rates. We also engineer stack systems for parts with short draw height and large machines to take advantage of projected area. These are very popular for packaging and container applications. Now, beyond those typical hot runners, we build systems for specialty applications like angle drops for highly contoured part geometry, such as automotive lenses. We build drop-in systems for simplified plate design and quick installation. We have side gates for narrow, long draw parts like pipettes or lure locks, and specialized melt delivery systems for finely tuned injection control with ultrashock. Now, hot runners require technology to monitor temperature and provide feedback about heater performance. And to do this, we design and build hot runner temperature controllers under our Altanium brand. And these controllers can be built for valve stem motion, timing, and sequencing control, and for mold action or cold half servo control. Finally, Husky provides services to support all those hot runners, cold decks, and controllers in the field. Now, these include refurbishment through a local Husky campus or on-site training and repair at your facilities. Our call desk provides support for reference information, drawing requests, troubleshooting, and spare parts orders. And we also have e-commerce for immediate quoting and expedited delivery of single drop and low cavitation systems. So as you can see, Husky has tremendous experience with injection molding in the medical, packaging, and CE markets. Our product portfolio is aligned to application advancements, and we provide advantages in several areas. Now, these advantages and advancements have carried over to the development of our own cold deck, and we offer the most advanced technology available for runnerless LSR molding. Its design is based on decades of field experience with valve gating and material delivery technology. This provides an out-of-the-box solution, allowing mold makers to focus on building cavities and cores, and molders to make parts with efficiency, quality, and reliability. But before talking about cold decks themselves, we should talk about LSR and get aligned on the basics. LSR is short for Liquid Silicone Rubber, and this is a common acronym used by many of us in the industry to describe the material family or to explain the molding application at its basic level. And there are several grades of LSR material out there in the world, just like we see for injection molded plastics. All of these grades have their own manufacturers, chemistry, rheology, and final part performance properties. And these properties can be similar to an elastomer, a rubber, or a urethane, such as a wide range of shore hardness, elasticity, and compressibility. But LSR is more than just a soft touch material. It carries unique performance properties, such as biocompatibility, durability, UV and chemical resistance, a wide thermal service range, and in some cases, transparency. That combination of some or all of those properties is what makes this material appealing for a wide range of modern product applications. I'm listing a few of them here. I'm not going to read through this list, but the point is it's a diverse list. And Husky is active in a majority of these markets, all of which are growing, so it's a perfect fit for us. The market for LSR parts has quickly developed over the past dozen years, with a CAGR or cumulative annual growth rate of 9% and estimated to reach $4.3 billion by 2028. Asia Pacific holds the largest portion of usage, with North America quickly catching up. So an increasing demand for implantables and advancements in molding technology have played a significant influence in that growth. But now let's talk about the technical stuff. More and more plastics processors are diversifying into LSR applications. So if you are evaluating or considering the LSR molding market, This should help you to identify and understand some of those challenges. Fundamentally, LSR molding seems similar to thermoplastic injection molding. Two mold halves are pushed together and held under tonnage. The mold cavities are filled with a liquid-ish material. That liquid changes phase and solidifies, and the mold ejects a solid part. This happens over and over again to meet an order quantity, and everybody hopes to make more money than they spend along the way. But for those similarities, that's like comparing baseball to cricket, football to rugby. They're similar, but they're also different. LSR molding has several fundamental differences, and I've categorized them here into 6 topics. The first topic or difference between LSR and thermoplastics is their chemistry and how they react to heat. The plastics, which many of us know and work with regularly, like polypropylene, polycarbonate, nylon, PET, these are all thermoplastics. When heat is applied to these materials, they melt and they flow, or they soften and they flow. When that heat is removed, they freeze and solidify. And this phase change is a two-way street, and it can be done indefinitely to a point. So we could say that an everyday example of this would be like chocolate or butter. You apply heat, it flows, you remove heat, it becomes solid over and over and over again. But LSR is a thermoset. So this is a liquid material, and it's undergoing, or it's continuously undergoing, a chemical reaction. As that reaction progresses, the material is curing or solidifying, and it is changing at the molecular level. So the difference between the melt or the liquid and the solid, it's chemically different. And if you're talking about polypropylene, that liquid polypropylene or molten polypropylene is chemically the same as the solid. So that means that the phase change is permanent, and there's no going back to that previous liquid state. So this is like an egg. When you apply heat to the egg, it solidifies, and it never, ever, ever goes back to being runny. Now, to respect the needs of both materials, the processing temperature environment is completely different. Your typical thermoplastic fills a cold cavity with a hot molten material. But LSR molding applications are the thermal opposite. That liquid silicone is kept cool, and it fills a heated cavity. And the heat from that cavity accelerates that chemical reaction and that phase change from a liquid to a solid. This even affects what we call the equipment to process these materials. When we are direct gating for a thermoplastic material, we are using a hot runner. And when we're doing the same thing for LSR, we are using a cold deck. Now, the method of temperature control for these processes is also very different. For plastics processing with hot runners, heaters are needed to maintain an elevated temperature, and thermocouples are required to monitor that temperature and ensure it doesn't exceed set point, lest it degrade that molten material. But for LSR, we need to minimize the material's process temperature in the cold deck and its nozzles. We want to stave off that heat, which accelerates the transformation from liquid to solid. And this is done with water and chillers. Thermocouples are still part of the plan, but they are used for monitoring and prevention. Processing viscosity is extremely different. LSR has an extremely low viscosity. We can say that it's similar to water, and it can flash in a clearance down to 1 micron in some cases. This makes our processing pressure expectation very low. Meanwhile, we're all quite aware of the much higher viscosity of molten plastic. I often describe molten plastics as flowing like cement, and this makes the processing pressure for some plastics extremely high in some applications. sometimes close to the upper limit of the injection molding machine and the other equipment. This case is extremely unlikely when molding LSR, but it's typically the cavity geometry which has almost all of the influence. Now, since the operating temperature of the materials are reversed, the engineering and the design intent of similar components are different when comparing a plastics hot runner to an LSR's cold deck. While a plastic is molten to flow, a hot runner's components increase temperature and they expand. Those components expand toward their operating position. That's physics. The plates which contain these components are kept cool, and they apply load based on calculated expansions. Their cooling maintains a consistent load on those components. So because the operating loads are greater than the assembled loads, component expansion must be carefully calculated and considered to prevent overloading and failure. But when molding with LSR and a cold deck, our cold material is contained in cold plates. Since the cavity is heated, it expands away from the cold deck or away from the cold deck's operating position. So in cold deck design, the assembled loads are greater than the operating loads. So on this slide, I have some icons which represent the temperature state while everything is running. These icons and their representation are really the core summary of this whole webinar. This is really important right here. These are super important concepts. So the load on the nozzles and the gates is just one consideration. Now, because expansion is happening along all three axes, plate alignment or interference alignment requires consideration. So the cavity and the cold plates are going to see differential expansion. So it's important to ensure awareness between the design pitch and the operating pitch. Finally, your cavity balance control is completely different. Hot runners can manage individual cavity balance through nozzle heater temperature and a temperature controller's interface. This modifies the rheology of the resin in the nozzle, and then every nozzle will fill the cavity at a slightly different relative rate. But LSR's extremely low viscosity magnifies any cavity-to-cavity variation. And the material chemistry does not allow you to manage viscosity thermally. So it's understood that cavity fill balance must have some degree of control by the molder, and individual cavity fill rate is managed mechanically. So when you have a multi-cavity system, and thanks to the extremely low viscosity of LSR, once one cavity fills first, it will continue to fill, and it may even flash the vents, making a part that's unacceptable. So Husky offers some different pieces of technology to do this, which we'll discuss later in our cold deck features. Now let's talk about the benefits of direct gating. Most of us here are familiar with solid runners. These are frequently experienced by people who assemble models because they're what hold all the pieces together. It's just marketed that that's there for the convenience of the consumer. One of the mold's core functions is to give material access to the cavity by way of the molding machine's injection control unit. And when this is done by machining a specific channel in the mold and removing the solid material that fills the channel each molding cycle, this is called a runner. And runners offer, or solid runners offer, a low initial cost to a mold and a shorter time to build it, but they also add overhead and operating costs to that mold as it runs through production. First, it takes extra material to make the product. Now with thermoplastics, that material can be reground, and it might even be recycled into the same process depending on quality requirements. But when molding LSR, that extra material is immediately scrap. Since LSR is a thermoset, once that material is solid, it is irrecoverable. It can never change back to a liquid due to its chemical change. And the cost of that material is literally thrown away. And with the nominal price of LSR going for $9 or $10 per pound, this is going to quickly add up during the runtime to fulfill an order. Not only does that solid runner have a direct cost when it comes to material, but there are several indirect costs. Those runners may require removal from the part by an operator, or they may require extra handling by automation equipment. And both of those activities add opportunity for error or breakdown. Once those parts and runners are sorted and separated, those runners still need transport to holding areas and finally to waste disposal. But by direct gating with the cold deck, so much waste can be eliminated. Not only is less material used, but so are all of the associated costs of runner overhead, handling, and disposal. By eliminating the runner, we can also reduce mold movement, and this improves efficiency and reduces wear and tear on your equipment. In one case, by using direct gating, we saw a cycle time reduction of 16%. So not only was waste reduced and less material used, but production output was also increased. So that's almost a full day's production every single week, or an extra 8 weeks of production every single year, all from the same work cell. Now, let's talk about what's needed for a cold deck to effectively manage LSR processing and what Husky has to offer as a cold deck solution. A cold deck has some key requirements for operating success. It's important to protect that LSR material from exposure to heat. This is because heat accelerates the solidification of LSR. And the chemical reaction to cross-link or solidify is always underway, and cooling slows that reaction. Now, by protecting the LSR from heat, we extend the maintenance interval of the cold deck. It's not if, but when a cold deck needs maintenance. And a cold deck's design should consider not just operation, but ease of maintenance and extending time between maintenance events. So cavity balance control is necessary to set up a good, reliable process, not just for the first run, but for any subsequent runs and variation between cavities, conditions, and work cells. Monitoring and risk prevention are extremely important, and this ensures the molding process and equipment are set up properly every single time. This also minimizes any risk for unplanned downtime due to a leak or an accidental cure event. And finally, it's important to eliminate the risk of leakage. That leakage could be LSR, it could be water, or it could even be air if you're using vacuum assist to fill those small cavities. Now, Husky's cold deck uses nozzles specifically designed for molding LSR with features critical to function. A water jacket actively cools each nozzle for its entire circumference and length. This ensures thermal uniformity and protects the material from heat. Commercially available seals are used to keep water inside the cooling network and off of your processing floor. And a valve gate with conical or taper shutoff manages gate quality. This shutoff, or this cone, this taper, also acts as an adjustable valve for finely tuning that cavity fill balance control. Each nozzle also includes a thermocouple. These thermocouples can be connected to any controller or any machine interface for monitoring, and their purpose is to ensure temperature is managed and under control. The gate also uses application-specific components. Our cold deck's tip assembly is constantly preloaded to the cavity. even as the cavity expands away from the nozzle as it approaches the process temperature. And this constant contact, along with those standard seals, eliminates any risk of leakage. And even though it's in constant contact, low conductivity materials are used to minimize heat transfer. This is going to protect the LSR from heat and extend that maintenance interval. And finally, the tip uses contoured flow channel geometry to work in tandem with the valve pin for cavity balance, adjustment, and control. And cavity fill balance is controlled mechanically, just like I mentioned earlier, and we enable this by managing the open or the back position of the valve pin. So by adjusting the pin position, we modify the flow restriction and the flow rate relative to other gates. Here, we're showing a section of 3 different nozzle flow channels. Each of them has their own valve pin, and each pin is at a different position. So at the left, we show the valve pin quite far back with very little restriction. At the right, the valve pin is quite far forward, restricting flow into the gate. So on the same system, more material from the drop at the left is going to fill the cavity than from the drop at the right. Now, to illustrate that better, I'm showing clearance or restriction, flow restriction with small pink circles. So at the left, you can see a larger circle that's showing you more clearance between the gate and the pin. And as we move to the right, we see smaller circles, and we see more of those smaller circles. Both of these show less flow area and a longer flow path through that flow area. Both of those make resistance. And I want to point out that this is about open position control. It has nothing to do with the media which is moving the valve pin. Now, we do offer different methods of drive media or drive method for valve gate actuation, and that can be through individual pneumatic pistons, or it can be done electrically through individual servo motors with our ISVG actuators. Split bolted manifolds are the standard offering for Husky's cold deck, and this allows for easy access to the LSR flow channels for that inevitable maintenance. This makes maintenance and recovery quick and easy. And because each application and mold of manifold are unique, the bolt pattern of the manifold is design specific and manages sealing to prevent leakage. Manifold flow channels are designed for geometric balance based on pitch and cavitation, and both manifold halves are water cooled to protect the LSR from heat and extend time between maintenance events. Thermocouples monitor each half's temperature to ensure cooling is active and under control. Now that concludes our presentation about LSR and cold deck technology. I hope everybody found something useful and informative from the webinar, whether you're looking to develop new products, diversify your business, or just learn something new. Thanks so much for watching. I'm going to hand control back over to Joe so we can finish out the time with questions and answers. Terrific. Now, if you're like me and you don't have a question until 3 hours later, I'll be happy to discuss anytime. Feel free to reach out to me through the contact information that I've got listed here. Back to you, Joe.
Excellent, Derek. And yeah, the contact information is there, and feel free to reach out. But we have a lot of time for questions too, so feel free to ask a question now and get it answered immediately. You can do that by typing in your question in the Q&A box. It's located at either the bottom or the top of your computer screen, and typing in your question, and we'll get to the questions in the order that they are received. Derek, let's start with one just generally about LSR. Why do you think LSR is becoming more prevalent in the molding industry? You outlined some of the reasons already, but maybe you can summarize a little bit of that here.
Yeah, I think I'll definitely touch back on those points. So like all of those things that I had said earlier, but it really, I'm going to say that LSR it's a lot like, it's a new material, really. And it's a material that, just like plastics were in the 40s, the 50s, the 60s, it's a material that offers unique properties and a unique combination of properties that are different from other currently offered materials out there in the world. I want to say that the biocompatibility property is that's a really, really big one, but it's also the combination of being a compressible material, and that thermal operating window is a really, really big one. Finally, the LSR has excellent chemical resistance. So that makes that combined with the temperature operating window, it can operate in high heat environments, and it can operate in very cold or sub-zero environments. And combined with excellent chemical resistance, that makes it a really good material for so many applications out there, where other materials just don't have that longevity.
Excellent. So you are seeing a rise in it being used in injection molding quite a bit, it sounds like.
Yeah.
Question that just came in: what are the gating location limitations using direct gating for LSR?
Those are going to be, gate location limitations. Those are going to be similar to any direct gating application. It's really about where you're going to put the gate and what are the other mold or part geometry features that are going to be in the way. So really, gating on a flat surface is going to be the best option, just like with any direct gating, and that's going to get excellent gate quality. You're going to have a nearly invisible gate in those cases. It's really difficult to put a gate right next to a protruding feature such as a boss or a rib, something like that, just because you need to have some space to allow for a nozzle, so that you can drop a gate there, but you also need space or distance for the clearances of that nozzle. Those clearances being really being for component clearance, and for insulating purposes.
Okay, excellent. So as long as you're aware of that, and I guess again pointing out to contact you if you have specific applications to discuss and how that will work within your project, I guess, anyway.
Right, absolutely. Yeah, every application is different. I never enjoy leading with the words "it depends," but it's in our industry. That's the name of our game. It always depends. There's always a reason to do every little thing, and for every single choice that we make along the way to make an object, to make an item. Those are all questions that have to be answered along the way, and those are all considerations that we have to be mindful of along the way too.
Definitely. Question: what is the impact of the technology on the LSR properties? Are there any specific requirements to the LSR itself in terms of what you're talking about as far as Husky's technology?
I would say that the only real impact is really where you can put the gate on a part. So it's what's the mentor that I had to learn about LSR from. I'm a hot runner guy from way back, and I've been in hot runners for 20 years. So when I was learning about LSR, he made a real point to say, stop thinking about this as a hot runner. And that's a really, really difficult thing to get away from. And it's really difficult to move away from thermoplastics and considering a material like LSR as a thermoplastic and using all of those plastics rules that we've all come up on when we're talking about or thinking about LSR applications. So the way that I'm understanding this question is with a hot runner and with thermoplastics. Thermoplastics are a material that's sensitive to a combination of time and temperature. And this is something in the hot runner industry that we always need to be mindful of for every application, whether we're talking about polypropylene, a PET, polycarbonate, a PEEK. We need to be considerate of how much material is at the melt state and how long is it there for. Otherwise, we can affect the properties of that final molded part. With LSR and with cold deck, really what we're doing is we are providing almost like a subway system from the machine's injection control unit all the way to the cavity. That material is undergoing a chemical change. And what we are doing is we are delaying that chemical change along the way. That material is also sensitive to heat, but the cold deck is not providing that heat. If anything, it's trying to remove that heat or prevent that heat from contacting that LSR, which is what would accelerate that chemical change, which is always happening once those two materials are blended and pumped through that injection control unit. So to summarize, I would say that the cold deck is not doing anything to change the material itself. It's actually working to delay that change, which is already happening due to chemistry and nature.
So there's no other special requirements that are needed for the LSR. Then it doesn't really affect that.
Yeah. To summarize, you want to keep it cold and you want to keep it from getting hot. So.
Right. Question about multiple drops. For multiple drops, is the cooling water flow through each nozzle done in a sequence or in parallel? And I guess second part of that too, can it be adjusted for temperature control?
Right. That's unfortunately one of those it depends answers. And that's going to depend on how close those drops are and how many are there. And so one could certainly try to one could try to individually control water flow to every single drop all on its own, but then it becomes a matter of space and resource. That's going to be a really difficult thing to do. So it's going to be a combination of both, and it's really going to depend on equipment available, machine daylight, tie bar spacing, mold size, all that stuff. If you're talking about a 2 or 4 cavity mold, it's quite possible that that your water circuits are all going to be in series. But if you have a really high cavitation system like a 32 cavity mold, you're probably going to have a combination of series and parallel, depending on just how close everything is. That's part of the fun of injection molding. Everybody wants you to make as many parts as possible in the smallest machine, smallest spacing, smallest footprint that you can. And everybody has really become an expert at doing more with less along the way.
Oh, certainly. So can it be adjusted for temperature control too, if needed?
Your temperature control is typically going to happen through a thermometer, just like you would with your mold temperature control, because you're controlling your cold deck temperature with water or with coolant. The cheapest of all coolants being water, right? So the best way to control that water temperature going in and measuring that water temperature coming out, that's all going to be coming through your thermometer network.
Okay, good. What's the smallest spacing between drops for your cold decks?
Oh, geez, that's going to depend also. Right now, with our individual drops, depending on if you're actuating, all of our cold decks are valve gated. We do not have an open gate. We stand by that. because that offers the best possible control that you can get. So our pneumatics, you can get down to, I want to say 2 inches from gate to gate. We're working on technologies to get those gates closer and closer all the time. So if you have questions, feel free to reach me at that contact information down at the bottom of the screen. Yeah, it's going to depend. I would say that 2 inches is a really, really good start right now, but that doesn't mean that we can't go lower for special occasions.
Sure, depending on the application again.
Yeah, right. Yeah, usually with more shut height, you can pack everything a lot closer. So you're going to sacrifice thickness for width, but so it's really a matter of choosing where your priority is and negotiating between all of that stuff at the same time.
Yeah, that makes sense.
When you think about good, cheap, and quickly, usually you're going to be 2 for 3, and that applies with nearly everything that everybody has to do, right? So if you can get all 3 at the same time, you're usually really, 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 really lucky.
Yeah, that's great. Hit the jackpot a little bit. You can do that. What's a similar kind of question? What is the minimum stack height of the cold deck?
That's not a number that I know off the top of my head, so okay. I'll have to get back to whoever asked that question.
Okay, fair enough.
Yeah, of course it's going to depend, just because it's really going to depend on if you're comparing a 2 cavity to a 32 cavity, and the big reason for that is you need more space for wiring for all of those thermocouples, and you need more thickness for preload management to make sure that all of your loads are applied for all of your nozzles feeding all of your cavities. But so that's going to increase your thickness because you need more stiffness to manage that load and to avoid your deflection, which is going to affect cavity wear. But I'll happily get back to anybody who wants to know more about that.
Sounds good. How much gate vestige is typically left with direct gating using the valve gate technology?
With valve gate technology, that's really going to depend too on not only your valve pin, but also your gate orifice. It's going to depend on angles. It's going to depend on clearances. It's going to depend on roundness, and it's going to depend on straightness and run out or cylindricity. I like to say that you're pretty good to be somewhere between 0.1 to 0.2 millimeters as if that's the first thing that you get when you're starting up. That's not to be unexpected. Perfect is what everybody wants, but all of those conditions are strongly affected by so many other things. You can definitely tune a lot of it out, but you've got to be very focused on quality of work and making sure that everything is just perfect or just so.
Sure. And again, I'll mention, if you want to ask a question, click on the Q&A icon box at the bottom or the top of your screen and type in your question. A general question here: do you have experience with molders and mold makers who have experience with traditional resins looking to get into LSR molding? And what are some of the differences they need to look out for?
Yeah. Absolutely. That's really why we're all here today. I was fielding questions pretty frequently, about once a quarter, from some customer or another asking, "Hey, we're interested or showing interest in molding LSR, or even having some LSR running in a plant or a clean room or something like that, and to see what could be done about eliminating runner waste." So we've received that question quite a lot. It's really what brought us about to developing the cold deck. And really the big thing is it goes back to always remembering that injection molding experience is very helpful in onboarding, but it's also to remember that this is that cricket to rugby, or cricket to baseball, or rugby to football transition. You're going to step on the field and things are going to be similar, but there are going to be some really, really big differences along the way too. Your thermal your thermal framework or your thermal arena is completely different. You're taking a cold material to fill a hot cavity rather than a hot material to fill a cold cavity. Your viscosities are going to be a lot different, and therefore the reasons why you're controlling your temperatures and your speeds are all going to have some relatively different purposes or reasons and effects as a result of it. So it's you can't just look at it and say, hey, I made some cavities and cores for polypropylene. Let's do that with LSR too. You certainly can. It's a great way to start, but it's also important to remember that extremely low viscosity plays a really, really big part of it too. I think in some cases, there are some molds that are built without any venting or really, really, really minimal venting, just because of because of that low viscosity of that material. So two real big things. I mean, I touched on 6 during the webinar, but I'd say 2 big things are going to be viscosity and temperature. Those are the big ones.
Yeah. But sounds like there's some good advantages to using it anyway, so you shouldn't be afraid to make
exactly
that, consider it.
Yep. You gotta spend money to make money.
Right. Exactly. When you restrict the valve open position to reduce the flow, are you not also increasing the shear, which induces the cure?
In that case, you are adding more shear rate. But in that case, the shear rate the shear or the friction that you are adding is not adding so much heat to the material that it is immediately curing. So, and it's also important to remember that restriction is happening right before filling the cavity. So all of that material that's going to flow into the cavity, it's not like you're doing it way back in your flow network. It's happening right there next to the cavity, and it's not going to be you're not going to have a restriction that is so tight that it is immediately curing the material and locking it up. You are not talking about glass-filled nylon here you are talking about a material that's still got an extremely low viscosity all along the way.
Okay, yeah, that makes sense. Question about micro injection. Is the cold jet concept suitable for micro injection?
I have seen it used in micro injection, though it's typically more for typically molding a runner that is a bit further downstream from the injection unit. So I've seen at certain very recent trade shows, there are some really awesome machine manufacturers out there who are running some demo molds. They are making little tiny parts that are smaller than plastic injection molding pellets. They're almost as small as the letters that you would see on a coin. And one of those is a 32 cavity mold that's out there, and it's molded with a 4-drop cold deck. So one could say, hey, isn't the whole point to direct gate? Well, yeah, that's true. But once again, it comes down to how much space do you have, how much height do you have, and what are you willing to sacrifice to get there? Typically, you're still molding a runner, but now you're molding several smaller runners, typically to keep everything all contained, rather than one giant solid runner which is a lot more cost because you have a lot more material that you're throwing away. So in that case, you're reducing your waste, not completely eliminating it.
Right. Yeah, that makes sense. How is LSR temperature controlled in a typical runner system without using the cold deck system?
Typically, your cavity temperature control is managed with heaters or with hot oil, depending on what the mold designer chooses to do. So, because at the end of the day, you need your mold temperature to accelerate that curing of the LSR in the cavity. And the only way that you're going to get heat into your mold is with electricity or hot liquid. So, but those are all questions better left to a mold designer. I am not a mold designer. I've seen a lot of mold designs in my day. I've looked at a lot of prints, but it is not something that I know how to do immediately. I've got lots of respect for mold designers because there are a lot of really intricate actions and a lot of really good reasons for making all of those choices all along the way, all of which I'm not fully aware of, but I know that everything that's done along the way is done for good reason.
Well, definitely. It's better to consult with the experts in that case.
Exactly.
Again, we have some minutes of questions left, and keep them coming in. We had some good ones so far. Again, type them into the Q&A box located on your screen. Can you further explain design considerations that go into effect when insulating the cold deck from the mold?
Certainly. So when you're a really good thing that I didn't really put too much detail into is separating the cold deck from the mold or from the cavity plate. So because you have a cold deck or cold deck plates, and you have a hot cavity plate. So it's best to have something in between. And the best thing to have in between is a board with insulating properties. Now, with hot runner designs, we provide insulator boards that typically go between the hot runner and the stationary platen of the machine. And that's great. It doesn't need to be that thick, and the strength of that material, it doesn't need to be that strong. It needs to be able to take a lot of tonnage. And if it deforms a little bit, no big deal. That's just a little less shy for the whole thing. But when you are molding LSR with a cold deck, what we supply an insulator board that goes in between your cavity plate and your cold deck. And that insulator board is made from a very special material that has a much higher compression strength than your typical hot runner insulator board. It's a lot thicker, and it also has much greater thermal resistance or lower conductivity along the way. There are with our cold deck insulator board design, there are no standoff pads. So that right there also helps to minimize the conduction or the flow of heat from your hot cavity plate to your cold deck. And that is also that's a pretty important feature to help to protect that LSR that much more from the heat that could cause it to cure somewhere along the way over time, ever so slowly.
Great. Why is stem control important? You mentioned that a little bit, and why is that critical?
Yeah. Stem control is important because that's what controls cavity balance. So with plastic injection molding, you have a material that is, you have a hot material flowing through a cavity, and it's a cold cavity. The walls of that cavity are removing heat from that liquid melt, from that hot melt, all the way from the gate to end of fill. And as it's flowing all the way to end of fill, some people call that the back wall. It is losing heat, it's losing temperature, and it's increasing in viscosity all along the way. Once you get to the vent, that vent is an extremely thin wall. If you think about it from a cavity point of view, sometimes a couple of tenths deep. That can be so shallow that is an impossibly thin wall to fill. Sometimes you could call that hesitation in some cases, but that wall is so thin that the heat from the mold, or rather the cooling of the mold, is stealing enough heat from the melts to cause that material to just go solid rather than to fill up in those vents. Where was I going with that?
That's important.
And so now when you are filling multiple cavities like that, you are increasing the resistance as you fill all the way up to 95%, 98%, 99.9%, that kind of thing. But when you are filling multiple cavities with LSR, that material is it is not losing viscosity, or rather, it is not increasing in viscosity as it flows to end of fill. Therefore, if you fill one cavity before you fill another cavity, now that material is still very flowy or anti-viscous, if you will. So you have the risk or the potential to flash through your vents. So you can have some cases where you have flashed cavities, and you can have other cavities from that same mold and from that same cycle that could be short or non-filled. So the whole point of valve stem position control is to finely tune that flow rate for each one of those cavities to make sure that they are all filling at the same rate for as best you can, in order to make sure that all of those cavities are neither short nor flashed.
Okay, excellent. Question that just came in. Cavity pressure is critical in thermoplastic material, but can cold deck technology bypass that control? Is that good to do, I guess, anyway?
I mean, I think that's a good question. I'm going to try to answer that the best way that I've interpreted, which is all cavities need pressure to fill. It's just that the pressure that one needs to fill a cavity with a material is dependent on a couple of things. It's dependent on the material itself. The material itself has a very specific chemistry, therefore it has a very specific rheology, therefore it has a very specific viscosity. Then your other piece to the puzzle is your cavity geometry itself. So how much pressure does the cavity require to make a full part with the material that you're trying to fill it with? Let's talk about polycarbonate for a second. That's a pretty notorious material with a very high viscosity. You can expect to hit the mid-20s, if not more, once you get your nominal wall thickness down to less than 1 millimeter, or 40 thousandths if you want to speak English. But when you have a material that flows like water, you're still also depending on all of those rules. You're depending on your cavity geometry a lot, and you're still depending on the viscosity of the material that you're trying to fill it with. So it's going to be, and we all live in the same world, and we all have to follow the same rules of physics, thermodynamics, chemistry, gravity, all of that stuff. So everyone has to do it, unfortunately, no matter how rich or poor you are. You got to follow those rules, right? Death and taxes. But the point being, there's a lot more pressure that can be used in an LSR and a cold deck application because the material is, it's not trying to work its way through 20 flights worth of screws and a really, really tiny machine nozzle orifice, and then a whole melt network that's also full of very viscous material or relatively viscous material, and now you're trying to fill a bunch of really, really thin walls. You're talking about a material that flows like water, and you're also going to fill some pretty thin walls, but guess what? Those thin walls aren't going to be nearly as influential on that pressure based on that viscosity. Certainly, you can try to fill some paper thin walls. You're going to need some other equipment to do that, like vacuum assist, but that's really still going to be a matter of viscosity and part geometry.
Great. Excellent. Well, that's about all the questions we have. And if yours wasn't answered, or if you want to, actually, and some of these were really application specific. If you want to reach out for more information, again, Derek's contact information is on the screen. I'll be happy to talk to you about particular applications and what can be done. I want to thank everybody for attending this Plastics News webinar, and I especially want to thank Husky Technologies for sponsoring it. And Derek, I want to thank you for a great presentation and for answering the volley of questions that came in anyway, and doing a great job with some of that. Finally, you'll find today's presentation by going to the webinar section of Plastics News website. You can watch the webinar again in case you missed something or want to catch up on a piece of it anyway. This presentation will be posted to our website within 24 hours of today's webinar. Again, I want to thank everybody for attending, and we'll see you at a future webinar. Thank you.
Thank you, everybody. Thank you, Joe.